Welcome to the Explainer. Today we're diving into what I can honestly only describe as a total engineering heist. We're going to look at how developers essentially used ancient number theory to tunnel straight under the incredibly rigid, unyielding constraints of modern blockchain architecture. If you've ever wondered how the next generation of decentralized finance actually works under the hood, well, you are in for a seriously fascinating ride.
I really want you to keep this massive, honestly kind of impossible-sounding question in your head as we go. How do you do trigonometry on a computer that literally cannot understand decimals? It sounds nuts, right? But the push for cutting-edge decentralized finance forced developers to answer this exact paradox. They basically had to resurrect division-free integer geometry, and the solution they found completely reimagines how we process math on a blockchain.
All right, here is our roadmap for the heist. 1. The EVM math wall. 2. FPU gambler versus ALU surveyor. 3. The square root integers. 4. The metallic mean family. 5. Simplifying with the GCD. And finally 6. True digital determinism. Let's get right into it.
Section 1. The EVM math wall, hitting the limits of on-chain computation.
To fully grasp this heist, we really need to understand the massive vault door blocking our path. We're talking about the physical architecture of the Ethereum virtual machine, or the EVM. The crucial thing here is that the EVM fundamentally prohibits native floating point math. That means it doesn't do decimals, and it absolutely has zero native support for continuous trigonometric functions like sine or cosine. Why? Well, in a decentralized network, tens of thousands of computers have to reach the exact same answer to maintain consensus. Absolute deterministic consensus is strictly required. If those machines just guess on tiny chopped-off decimals, consensus breaks instantly, and billions of dollars could literally just vanish. And trying to fix this on-chain with standard approximations, it causes severe gas spikes.
Moving on to Section 2, FPU gambler versus ALU surveyor, two paradigms of silicon processing.
To truly understand why this EVM math wall is such a huge problem, you kind of have to personify the hardware a bit. Think of the computer's physical brain as having two very distinct personalities. On one side, you have the floating point unit, or the FPU gambler. It's incredibly fast, sure, but it relies on spatial approximation. It's basically throwing darts at a board, relying on lossy, probabilistic guesswork, and it is fundamentally non-deterministic. On the exact opposite side, we have the arithmetic logic unit, the ALU surveyor. This one is all about strict, bit-perfect, discrete integer logic. 1 plus 1 is exactly 2 every single time. It provides universally verified truth. Blockchains absolutely require that surveyor, but complex math? That usually relies on the gambler.
And this brings us to what researchers call the wood chipper effect, which brilliantly illustrates the catastrophic fallout of using that FPU gambler for complex logic. Basically, when non-deterministic hardware relies on floating point guesses, the exact mathematical identity and the provenance of that data is permanently destroyed. It's like throwing a beautiful fruit basket into a giant wood chipper. You might know what went in, but you can never perfectly reverse engineer that pulp back into the original fruit. In finance, that kind of data leak leaves liquidity pools incredibly vulnerable to rounding errors and exploits.
Section 3. The square root integers, tunneling under the wall.
So how do developers bypass this? This is where the heist really comes together, specifically with a groundbreaking discovery found in the best ape square roots repository. Instead of dragging around heavy, bloated legacy methods like Taylor series or Cortic algorithms, which, let's be real, is basically financial suicide in terms of gas, and instead of dragging around complex double sequence math that creates high information debt, developers found a wildly elegant shortcut. They brought in a single linear recurrence. It's a natively gas-efficient, elegant, iterative hack that tricks the computer into calculating nearly perfect square roots using absolutely nothing but whole numbers. Here is exactly how it works in practice. Step 1. Input the target irrational number you want to approximate. Step 2. Run that single-sequence linear integer recurrence. By creating a ratio of just the current step against the previous step, it generates an unbelievably accurate approximation. And step 3. You just stop the sequence generator the second that exact accuracy level is hit. That's it. No decimals, no FPU gambler, just bit-perfect integer logic tunneling straight past the EVM's limitations. Section 4. The metallic mean family, ancient geometry resurrected.
Now, the math powering this natively efficient system isn't exactly new. Actually, to pull this off, developers had to reach way back in time. By utilizing Faraday-Spinato's metallic mean family, developers can build completely stable integer ratios, like the copper ratio, to approximate complex curves. This mathematically immunizes the system against numerical drift. The coordinates lock into predictable patterns,
bouncing safely between stable integer pairs, rather than forcing a machine to guess continuous curves.
Just to put this into perspective and give you a sense of the precision we're talking about here, using these integer ratios, at just level 2 of the sequence generator, the error rate drops to an astonishing 0.00485%. I mean, there is almost no error. They hit practically perfect mathematical fidelity, using absolutely nothing but pure integers.
Which brings us to Section 5, simplifying with the GCD, the ultimate compression tool.
But wait, there's a catch, right? Generating these incredibly accurate ratios means the integers get absolutely massive. And remember, we are still trapped inside the strict computational limits of the EVM. So how on earth do we fit them in? We use the greatest common divisor, or the GCD. But in the best apes square root integers repository, the GCD isn't just some dry math formula. It acts as the ultimate compression tool. It takes those massive integers generated by complex approximations like the copper ratio and simplifies them down to their leanest possible form. It's the critical mechanism that sneaks those fractions safely past EVM gas limits, which drops the metabolic energy cost of the network dramatically.
When you stack the whole shebang up, the single sequence recurrences, the metallic mean geometry, the GCD compression, you get a 74 times reduction in metabolic energy compared to legacy floating point calculations. Think about that for a second. 74 times. That is not just a tiny marginal improvement, that is an absolute hardware paradigm shift.
By resurrecting this ancient math, they didn't just bypass the EVM wall, they absolutely obliterated the energy cost. The energy required to perform one of these exact division-free coordinate rotations hits a staggering rock-bottom floor of just 0.05 picojoules per operation. It's wild.
Finally, Section 6, True Digital Determinism, Verifiable Truth on Silicon.
Let's zoom out for a minute and pull all these technical details together because the macro impact here goes way beyond just saving on gas fees. By moving entirely away from spatial approximation and that FPU gambler and fully embracing the pure integer geometric rigor of the ALU surveyor, we achieve absolute, strictly unbiased, bit-perfect orientation. We essentially unblend the smoothie. We restore the exact provenance of data, guaranteeing perfect mathematical fidelity across tens of thousands of decentralized machines simultaneously. We achieve true digital determinism.
There's a profound quote from the architecture documentation that I think just hits the nail on the head. The human pilot applies the intent, but the agent cell executes the sweat. By meticulously mapping our fluid human intent onto exact, verifiable integer sequences, we build a flawless semiotic bridge directly to the deterministic silicon of the machine. We command the math, and the machine executes it perfectly, without a single guess.
So we've traced this incredible journey from rigid EVM constraints past the messy guessing of floating point math through ancient geometry and clever GCD compression all the way to absolute, verifiable truth on silicon. I want to leave you with one final provocative question to chew on today. Now that this bridge between digital truth and physical reality is wide open and highly efficient, what will you program physical reality to do? Thanks so much for hanging out with me for this explainer. Keep learning, keep building, and I will catch you next time.